Welcome to this video in which we're going to solve exercise 3. In this exercise we're going to use the double mass curve to analyze a series of annual precipitation and correct the data in case it is needed. This is an extension of exercise 2 in which we used also the double mass curve, but in this case we're not told which is the error in the data, so first of all we have to identify errors. As usual, in the main folder, notebooks, you have exercise 3 with precipitation. Okay, there's an incomplete version in case you want to follow that one. I'm gonna start with a new notebook and rename it exercise 3 solution. Okay. First thing first, we need to import packages, so the regular packages numpy, pandas, and matplotlib. And we're gonna use Seaborn to make the plots look nicer. Okay. If you remember from exercise 2, also about the double mass curve, we needed from SciPy optimize to import function curve fit to fit the parameters of a function that we're gonna linear regression actually. So now we imported the data that we need. The packages that we need. Let's start importing data. So first step of all, I'm gonna skip explaining the double mass curve. If you need an explanation, just go to exercise 2. So import data. Okay. The data is in our main folder, data, rainfall data, the Excel file. And we need the heat exercise 3. Okay, so we need to import these values. Good. If we get back here, so to import the table from Excel, we use pandas, read Excel, and then we have to specify the file we want to read, which is in data, and it's called rainfall data XLSX, and the sheet name we're interested in is exercise underscore 003. Okay, let's make the first column the index, so index call first column. And we'll save the data as data 3. Let's see just the first few lines. We're going to create a vector which is called gauges, which is the name of the gauges from data 3. So columns, we just create gauges. And then remember, first thing to calculate the double mass curve, we need to create a new column with the average precipitation. Average. So data 3, we create a new column called AVG for average, and this is just the mean across columns. This is axis 1 for columns. And now we have data 3 head. We created this new column which is just the average of the 5 stations. Okay, we have imported the data, and now let's plot the double mass curve. So far we have plotted or created figures with only one plot in the figure, but now we want to plot the 5 extensions in the same figure. So for that we're going to use the function subplots, and we can specify the number of rows and the number of columns. So we need to create at least 5 plots. So let's give it 2 rows and 2 columns and 3 columns, and then give a fixed figure size equal to 12 by 8, for instance. So if you run this, you see that we created 6 plots with 2 rows and 3 columns. This is what we set here. And we need to fill data into this. Okay. For that, we're gonna do a loop across the stations. So I'm gonna show you one interesting thing. This axis has it's a vector, an array with 2 rows by 3 columns, so exactly one object for each of the plots. So if we want to plot in this first plot here, we have to access axis 0, 0, for instance, and then make a scatter plot with a value of 0 and 5. So we create a point here. If we want to plot in, for instance, this plot here, this will be line 0, row column 2, and we will create this here. Okay. Different way to do this is to create something called ax, and then you put axis 0, 2, and then you just plot everything to ax. Okay. So now, we need to know this to create the loop. Ax in zip gauges and axis flatten. So what I'm doing here is just making a loop across gauges and axes. So let's print what this is doing, gauge and ax. So the first time we enter the loop, it gets to gauge A, and it's gonna plot everything into this first plot here. Second time we enter in the loop, we're gonna work with gauge B, and we're gonna plot it here. Third time, C, plot it here, etc., etc. So first of all, we're going to plot a line of slope 1, because this is going to help us to find breaks in the line. So ax plot, and we're going to plot from point 0, 0 to point 800, 800. And let's give it a style with dotted line and black color, and we can give a label which is going to be 1, 1 line. So now we have created these lines here for these 5 plots. We need to skip this last plot because we don't have a station for that plot. So we can do that by we access this axis and then give row 1, column 2, and we set the axis off like this. Okay, so now we only have 5. Let's plot the double mass curve. Double mass curve. And then to plot it, remember we have to create the cumulative sum of the average against the cumulative sum of each of the stations. So we get into data 3 average and cumulative sum, and data 3 to the gauge that we're working with in each instance of the loop, and create the cumulative sum. And then we're gonna give a line style with dots, and line both, and then a label which is the double mass. Okay, then we can create a title to each of the plots, which is going to be the name gauge and the name of the gauge. And lastly, let's set the legend. We will put this here. Okay. So we get this plot here. 1 plot for each gauge, and we see the double mass curve. Like this, we can start identifying possible errors. So for instance, gauge A, we don't clearly see a break in the line, but we see that the slope is higher than 1. This means that precipitation in gauge A is larger than average. In gauge B, we see kind of like a belly in the middle of the curve, so there might be some troubles in there. In gauge C, we see a perfect line almost fitting the 1-1 slope, what means that gauge C has precipitation similar to the average in the region. And then in gauge D and gauge E, we see two clear breaks in the line. So one will be here for gauge D, and one will be E for gauge. The other one will be this one for gauge E. So this is just our basic identification, but we can improve this and try to identify errors automatically. That will be the next step in the exercise. So identify errors. We're going to create an algorithm that fits linear regressions to the lines and find in which year there might be a problem for each of the stations. First thing we need is the linear regression function. We have created that in exercise 2, so we can just go to exercise 2, which should be here, for instance, and we can look for the linear regression here. Okay, so we can just import this linear regression, put it here. Basically, we're creating a line with no intercept, so only one parameter, which is the slope. And I'm gonna start doing the algorithm just for one gauge as an example. So for example, gauge A. Okay, we define the gauge. So gauge is going to be A, and we're going to define an error threshold, which is error equals, let's say, 0.1, for instance. Basically, remember how we identify errors. Let's say we're in gauge A and we're in this year, for instance. We're gonna feed a line to these values here and then feed a regression to these values here. We identify an error if there is a difference between the slopes of these two lines larger than the threshold that we set. Okay, so basically we're going to feed the regression for the previous series. So 1, for instance, remember we're going to use curve fit from SciPy optimize. We need to input a function, which is this linear regression here, and then we have to input the x and the y, x data and the y data. X data is going to be from that data 3 location up to 1 year. Okay, so let's set here a year 1938, for instance. And the average, this will be the x data, and the y data we can just copy, and then we have to do the cumulative sum, very important. And then the y data, we can just copy these and change, instead of the average, we just want the gauge A. Okay. Remember that curve fit linear regression, and year is 1938. Okay. Curve fit gives us two vectors. One is the parameters and one is the performance. So we only care about the first vector, which is the parameters, and we only care about the only value that we get, which is the slope. So this will be slope for the line 1. Okay, we can copy this and fit the regression for the posterior series. So M2, and now we're gonna fit from that year on, and from that year on. So in this first cell we are feeding the line up to that year, and in this second cell we're feeding the line for this year onwards, and we get a second M2. So this will be M1 and this is M2. Okay, and we identify that this is an error if the absolute difference between M1 and M2 is larger than the error that we estimated. So in this case, it is not. We can see clearly that this is around 0.03, which is not larger than 0.5. So there's no error. Okay. Let's plot it like this. If there is an error, just in case that this is true, print year M1 and M2. Okay. We have done just this for one single year. What if we just merge it all? We can skip this, and this, and this, and this, and then we put all this into a loop. For year in data 3 index, and so we create the whole data. Okay, it raised a warning about that it couldn't fit the values for some years, but that's just because one reason here. So obviously if you just, the first year that we enter here, you're gonna fit a line to only one value, so that's gonna raise an error. So let's put here, so this means that we're gonna start from this point, the third point, the fourth point here, and create a line with this against this other line, and we're gonna end in this other point. So the fourth from the last, and we're gonna create a line from here and here. Okay. According to this, there are no errors in gauge A. We can repeat this for any other gauge. For instance, we can just delete this, which is an example. Okay, so gauge B, there might be some errors. Gauge C, no errors, etc., etc. This is not ideal, but you can clearly see how we can improve this. So let's do it for loop for all gauges. So we're going to create a new function, which we're going to call identify errors, and then we have to provide to this function the data for the gauge, the data for the average, and then an error threshold, which is 0.1, for instance, the same that we've been using. We should give a help like identify possible break points in the double mass curve, and then introduce the inputs and the outputs. I'm gonna skip this part. You have it perfectly written in the complete exercise, which is here, okay, which is so here, okay. And then the function is just going to do this. We can copy, paste. Remember to press here tab, so there must be an indent for a for loop, and a first indent for the definition of function and a second indent for the for loop. Basically, every time you put a column, it needs an indent. And now we have to change this. So we're gonna get into data gauge, and up to that year, we're gonna calculate the cum sum, and then here, sorry, this is the data average. That's the X, Y axis, and this will be data gauge and consum, okay, and the same here. So data average, and we are gonna get from that year onwards. We can just delete this consum, and then data gauge consum. Print. Perfect. So now we create a function, and we can easily remember that gauges is the name of each of the gauge, and we can loop print to know in which page we are. Gauge. Okay, and they identify errors. Theta 3 average against Theta 3 for our gauge, and then we're gonna set an error of 0.1 and print a blank line just to separate calculation for each of the gauges. So we're getting into gauge 1, doing all this performance that we saw here on top, that there are no errors, so no errors were raised. Then we get into gauge B and we see all these errors. So there might be possible errors between 1929 and 1939. Gauge C, no errors. Gauge D, we see an error in 1930, and gauge E, we see errors on possible errors between 1929 and 1939. So the main result of this part of the exercise is that we have identified errors in gauges B, D, and E. So we have identified errors in gauges B, D, and E. And now we have to get to these stations and correct the errors. So first, let's start with gauge B. And we're gonna start by analyzing the series before we get into analyze the series. So remember that these are just possible errors, but it doesn't mean that all these years has an error. So first we have to get into exactly data that we're interested. So set gauge and breakpoints. Gauge is V, and the breakpoints, we're going to create a list, and we see that there are errors from 1929 to 1939. So the breakpoints could be 1929 and 1939. 1929 and 1939. Okay. And we can plot the double mass curve. So we create a figure with a size 5 by 5. Remember that this axis sets an equal scale for both axes, x and y, and then we can plot the one line, so a line of slope 1 with a dashed line with color black, and then we can plot our double mass curve. So Theta 3 average consume against Theta 3 for our gauge consume, and we're gonna give it a style with dots and lines both together, and label it original for original series. And then we're gonna plot our breakpoints. So we can just copy this here. Okay, but we're just gonna get into the breakpoints, breaks, and the same here, lock breaks. And in this case, the line style is gonna be just dots, and let's label it breaks. If we print the legend, sorry, this was semicolon. Okay, I'm missing one comma here. Okay. Oops, and this is an error too. So this is the same plot as the one that we had on top for gauge B, but we have included the break lines. Still, according to our algorithm, there is a break line here in 1929 and another break line here in 1939. So there should be 3 slopes. One before here, before 1929, one before 29 and 39, and one after 39. But if we inspect this now, we can see that probably the breakpoint is not 1929 but 1930. And here the same. It seems that this is a line and this is another line. So probably the best year here is 38 instead of 39. So let's reset the breaks points. This is a very subjective analysis. So you may not get the exact same results, but the idea should be the same. And now we have to fit 3 lines, one to up to 1930, another one between 1930 and 1938, and the last one after 1938. Let's copy this here. Okay. And then Shift Tab to put it here. So the first slope will be for data average up to breaks 0, and here Theta 3. Okay, let's save this and get into average, and now we can copy this and put it here, and instead of average we're gonna use gauge. This will be fit the regression before the first break point. Now let's fit the regression between break points. So we can just copy this here, call it M2, and now it has to be from breaks 0. So from 1930, sorry, to breaks 1, which is 1938, and the same here. And finally fit the regression after the second break point. So this is 2. And now we're gonna fit the regression from the break 1, which is 1930 onward, and from break 1, which is 1930 onward. So there are plenty of errors. We're missing data here, so we're gonna miss it here and here. M1, M2, and M3. Now we have 3 slopes, one for the first line, another one for the second line, another one for the third line. Well, according to this, we have to assume now which of the 3 periods is the correct one, and we're gonna assume that is the central part of the series. 1, because it's the longest period, and 2, because it's the one with the closest slope to 1. Okay, so assuming that that is the correct series, we are gonna correct the other one, the other 2 parts of the series. We have to create the correction factors. Correction factors. From the previous exercise, we know that the correction factor, for instance, the 1, 2, representing the correction factor for the segment 1 according to the segment 2 is the slope of the correct part, which is M2, divided by the slope of the incorrect part. And then the factor for 2, 3, which is the correction factor between segment 2 and segment 3 will be the correct slope, which is M2, divided by the incorrect slope, which is M3. And we can see what is the values of this. Factor 2, 3. So we are going to multiply these values in the original series by factor 1, 2, which is 0.91, and we're going to multiply these values here by factor 2, 3, which is 1.13. So first we're gonna copy the original series and save it in a new column called b underscore and date 3 and make a copy of gauge b. Okay, important to make a copy. Then we're going to correct period before the first break. So we get into date 3 and then in b up. So up to the first break 0, we correct b underscore. How do we correct it? By multiplying by the factor. So we multiply by factor 1, 2. Now I have corrected the first part of the series. We copy, correct the period after the second break. So now we're gonna correct from the second break. This is with S onwards. That's the 2 points for b underscore, and we multiply by factor 2, 3. Okay. So far we should have corrected the series. Let's check it visually. So we can just copy the plot and put it here, and we're just gonna add one more line. So we can delete this and we're gonna put this here. And now instead of plotting gauge here, we're gonna plot gauge plus underscore, and the label is going to be corrected. Good. So we see the original series, we had that belly here. Now it's more or less a straight line up to the end. Good. We can check again for errors. So the function that we created before, errors, data 3 b underscore, and data 3 average. Remember shift tab to get the help. We could also set an error, but we're always working with error 0.1, so by default it's 0.1, and there are no more errors. So this means that we have done our job with gauge B and we have corrected the data. I'm going to stop here the video, and in a following video I'm going to correct the other stations.